Hi, hello everyone. Let's do another problem and learn something really basic about electric field. So first of all, you should know some vocabulary. So here is some vocabulary that will be helpful to us. So we're gonna call something called source charges. So I'm going to label some charges as source charges and another one called field charge. So what is a source charge? A source charge is first let's say field charge. Field charge is what you are trying to work out the dynamics of, or trying to understand how it's responding to whatever environment is in. And source charges are all the other charges. So in this problem, we're interested in the motion of this charge. Then this charge will be this will be the field charge, and all these other charges, those other charges, they will be the source charge. We're just going to call them like that, and you will learn a little bit why we want to call source charges and some charge as a field charge. Okay. Now, second thing we want to the third thing we want to know is what is an electric field. Okay, and we're going to learn various ways of looking at electric field. So let's look at an example. So if I have these charges, a whole bunch of charges here, these are source charges, and let's label them 1, 2, 3, like Q1, Q2, Q3, and maybe the last one is Qn. Okay. And then I have a field charge, maybe over here, some field charge. Let's label this maybe capital Q. Okay. And we want to study what's the force on the field charge. So force on the field charge. If you write down from Q1, there will be force in that direction. From Q2, there will be force in that direction. Q3, the force will be in that direction. These are positive, and so this is positive. Then this will be the direction. This will be in that direction. So if it's negative, they just flip the direction. But we know the formulas for these forces, for each one of the forces. So it will be for on field charge, Q is just going to be K, which is you remember K equals to 1 by 4 pi epsilon naught, right? K, then you have a field charge times field charge times unit vector over R. Let's call this R1, let's call this R2, let's call this R1 to the field charge, let's call it R1 to F, R2 to F, R3 to F. So this field charge, this location be F. So R1 to F times Q1 over R1 to F square plus KQ charge at 2, charge 2 not to F, 2, charge 1, charge 2, but unit vector from 2 to the field point over R2 to the field point square, like that. Now let's pull the common q from all of this. Okay, so we're going to pull the q out, and we'll have a k q1 u1 hat 1f over r1f square. And this is the direction, and this the magnitude, but with the sign, sign of this. So direction can be in the direction of this or opposite to it, depending on the sign of this guy. Plus k q2 unit vector from 2 to f over r2 to f square, plus the last one will be kqn u hat n to f or nf square. Now this thing, we call it electric field of all of these charges, electric field of all the source charges. So this part we'll call electric field of source charges q1 through qn, electric field at the location of field charge electric field of the source charges at the location of the field charge. Okay, or however you want to say it. So at this point, these guys have this algebraic thing associated with that, and it's called electric field of the source charges at the location of this. So we can just call this guy E. This will be a vector, so we just call vector. And so you can see that it's very easy to convert electric field. If I know electric field is multiplied by the field charge, and I'm going to get the force on the field charge. And that's what this problem is. Okay, and the formula is basically everything other than for each one of the charges is like that. Each one of the charges, just factor out from the Coulomb's law the field charge from the expression. Okay, so it's going to be calculationally almost like the identical to working out Coulomb force. Let me erase this and work out the numerical value that we're going to get over here. So electric field, let's work out with a. So we want electric field of source charges at point C. So electric field at C will be K QA over this distance. So let's call it dA square, and then it's going to have a unit vector u hat a like that, u hat a plus k qb over db square u hat b plus k qd over dd square u hat d. And so from B is going to be that direction, from D is going to be that direction. Now if we use a XY coordinate system, let's call it Y, and let's call this guy X, then we will be able to get this guy will simply be I hat, this guy will simply be J hat, and this guy, you can work it out, is going 4 this side and 3 this side, and this is 5 centimeters this side. So this will simply be 4 over 5 I hat plus 3 over 5 J hat. So that's going to be that. And this is 5, and this is dB from here is 3, so this is 3 square, 3 centimeters square, and this is 4 centimeters square, and this is 5 centimeters square, right? So let's write this whole thing out. So k is 9 times 10 to the power 9 for k, and QA is 2 coulomb plus 2 times 10 2 microcoulomb, so 10 minus 6 divided by 5 times 10 to the power minus 2 squares. Everything into MKS units, and this one just 4/5 I hat plus 3/5 J hat. Now this would be this guy would be very similar. It's going to be 9 times 10 to the power 9 times, but QB is negative, so it's going to be negative 3 times 10 to the power minus 6 over 3 times 10 to the power minus 2 square, and this is going to be simply J hat. And from here to here is going to be, this whole thing will be same because all of, except this this distance will be different. So let's try it down rather than not jump too much, because minus 3 times 10 to the minus 6, but this is going to be 4 times 10 to the minus 2 square, and this is going to be I hat. Now you can look at all the powers of 10. Everything has a power of 10 to the power 7. 9 minus 6 is 3, and then plus 4 comes up, that makes it 7. And the unit of this will be Newton over Coulomb, because as you know, we had a force equals to field charge time electric field, and so if this is Newton and this is Coulomb, then this is Newton over Coulomb. So this 10 to the 7, we just write down 10 to the 7 times 9 times 2 over 25, 4 over 5 I hat plus 3 over 5 J hat, and this will be 10 to the 7 again times 9, and this is going to be minus, because of minus 9 times 3 over 9, so you can cancel that out. J hat is going to be minus 10 to the power 7 times 9 times 3 over 16 I hat. Okay, so we have, you can see I can just simplify all of this with that, and so I'm going to get some EX I hat plus EY J hat, and I'm just going to work it out and write the answer down here for you. See, EX is simply 10 to the power 7 times 9 times 2 times 4 over 125 minus 9 times 3 over 16. That's the EX, Newton over Coulomb, and EY is going to be 10 to the power 7 times 9 times 2 times 3 over 125 minus 9 times, that's actually just a 3 because 9 got cancelled, Newton over Coulomb. So working this out, let me get the numerical value and I'll be back. Okay, so I simplified this by calculating, and then I get for the EX I got this, and for EY I got that, and write this answer. Maybe that's good enough answer for some purposes, we can convert this just like any vector into a magnitude and a direction, and let's try to do that. Okay, so what's the magnitude? So this vector is in the minus 1.11 here and 2.5 over here. This is pointed in that direction like that. There's the x and y. So this will be the magnitude part. E at C is square root of this square plus this square, and 10 to the 7 is common, so I don't need to do that. This whole thing will be times 10 to the power 7, and it's going to be 1.11 square. You don't need to carry a negative because square root is going to be the same thing. And so this will be in the unit newtons or coulomb, and I worked this out, and it's 2.81 times 10 to the power 7 Newton over Coulomb. And because this is in the third quadrant, we just get a degree theta from the negative x-axis when you do arctangent. So it's going to be 2.58. Because 10 to the 7 is common, it's going to cancel out 1.11. And let me work that one out. So a tan of 2.58 to 1.11, and I should convert this into, I need to put math dot because I'm using math library. So 66.7 degrees. This becomes 66.7 degrees. So that's the answer. So you can write down into analytic form. You can write down in magnitude and direction. So we got done one. To get 2 is very easy because electric force is just this charge times electric field. So I can write down using magnitude. I can write down over here. Let's write down magnitude. The direction will be, if it's positive, then it's remain positive. So F on C is QC times electric field at C by other charges, by sources. Okay, so this one is positive, then the direction will remain the same. Otherwise I'm going to have to add 180 degrees to it, right? So let's see, we are going to do right now is going to be 2 times 10 to the minus 6 times 2.81 times 10 to the power 7 Newton, and this is going to be, the direction will be 66.7 degrees. And so that turns out to be, let's see, so it's 10 times whatever the number to multiply, let's multiply it. So 20 times 2.81, I should have done it in my head, 56.2 newtons. So this is equal to 56 Newton, comma 66.7 degrees. Now let's see what will happen. What if QC was minus 2 microcoulomb? Well, we'll do the same thing. So this will come out to be like this, but when you multiply, it's going to be minus 56 Newton and 66.7 degrees. But this is not correct. This is not the way you should write it. You should say, I'm going to make it positive and make this guy plus 180 degrees. Okay, so that's going to be 56 Newton and that has to do with magnitude is always positive. And if I add 180 degrees, it's going to be in that direction. So this is theta, then that's theta, right? So if this is 67.7 degrees, then that's also 60. Yes, it will look like I went from here and I did that, and it should be also 66.7 degrees. So this is 66.7 degrees, but this is in first quadrant, and this answer is in third quadrant. Okay, sometimes this is really important to notice it, which quadrant you are. You just note that down so you know the direction in space. Okay, and it makes sense. If this was negative, then these guys are, in that direction, and that dominates, and it's in the first quadrant. If this is positive, then they're being pulled in that direction mostly, and then repelled here a little bit. And so the net effect is in that direction if it's positive. But it's negative, it's going to be exactly opposite direction, and that's going to be in the first quadrant. Okay, I think this is a very instructive problem. So you learned a couple of things. Let me just make sure we can write this down. So one is we should know what source charges are. We should know what field charges are. And then there is a kind of like a separating out of the Coulomb's law into electric field, and in this fashion. And we will talk about electric field more in the next video. It's a very important concept, and through Gauss's law really helps you attack much more difficult problems, right? Than simply adding up the Coulomb forces. There are a lot of analytic approaches become available to you when you start to think in terms of electric field. It has a lot of benefits, and it's going to show up as we progress through the concepts of electric field, electric force, electric potential, and so on and so forth. So I'll see you in another video. Bye.